So if the universe, all of space and time, burst into existence from a point of unimaginable density and then inflated faster than the speed of light, it forces us to ask the one question that feels almost forbidden. What did it expand from? We're forced to confront the concept of nothing. When you or I think of nothing, we probably picture an empty box, a perfect vacuum. We imagine taking a sealed container, pumping out every last atom of air, shielding it from all light and cooling it down to absolute zero, the point where all motion ceases. We'd expect to find nothing, just still dark, perfect emptiness. But the universe at its most fundamental level simply doesn't work that way. It seems reality has a deep, profound allergy to true nothingness. What quantum mechanics revealed to us in the early 20th century is that this empty is not empty at all. It is a seething, churning, violent ocean of potential. We call it the quantum vacuum. This isn't just a nice metaphor. It is the physical baseline of reality. It's the ground state of the universe. And if you could zoom in on this nothing, you would find it boiling with energy. Why? It comes down to one of the most powerful and strangest rules of existence, the Heisenberg uncertainty principle. Werner Heisenberg discovered that there is a fundamental fuzziness built into the fabric of reality. You cannot, for example, know exactly where a particle is and exactly how fast it's moving at the same instant. The universe just won't allow that level of certainty. But this principle doesn't just apply to motion and position. It also applies to energy and time. You cannot know the exact energy of a system during a very short period. Because of this built-in uncertainty, empty space is allowed to borrow energy as long as it pays it back almost instantly. And what happens when you have a little blip of energy? Well, thanks to Albert Einstein's famous equation E equals mc squared, energy equals mass times. The speed of light squared energy can spontaneously become mass. It can become particles. So in this quantum vacuum all across the universe, pairs of particles are constantly flashing into existence. We call them virtual particles. An electron and its antimatter twin, the positron, might pop into reality. They exist for a fraction of a quadrillionth of a second, just long enough to exist before they find each other and annihilate, paying back the energy loan they took from the vacuum. This boiling of virtual particles isn't just a mathematical fantasy. We have measured its effects. There is a famous experiment called the Casimir effect. If you take two perfectly smooth uncharged metal plates and place them extremely close together in a perfect vacuum, so close they are only micrometers apart, a strange thing happens. They are pushed together by an observable, measurable force. Why? Because the empty space outside the plates is boiling with all kinds of virtual particles pushing on the plates from the outside. But the tiny gap between the plates restricts which particles can pop into existence. Only virtual particles with very specific short wavelengths can fit. This means there is more quantum pressure on the outside of the plates than on the inside. That physical push that force moving two objects in an empty room is the force of nothing. It's the tangible pressure of the vacuum energy itself. This is fascinating on its own, but it becomes the most important concept in all of cosmology when we connect it back to the Big Bang. This vacuum energy isn't just a curiosity, it is the reason we are here. Back in that first fraction of a second, the universe was this tiny, incredibly dense quantum vacuum. It was boiling with these tiny random energy variations. We call them quantum fluctuations. They were just subatomic blips in the energy field. In a normal static universe, they would just appear and disappear, averaging out to nothing. But the universe wasn't static. As we discussed, it underwent inflation. It expanded exponentially, stretching faster than light. And as the fabric of space itself stretched, it grabbed these tiny fleeting quantum fluctuations and stretched them too. It expanded them to macroscopic and then astronomical scales. A tiny blip of energy that should have vanished in a split second was suddenly stretched to the size of a galaxy. Those tiny variations in energy became the first real variations in density in the new universe. The slightly denser spots, the hot spots in that early soup, had slightly more gravity. Over millions and then billions of years, gravity did its work. It pulled more and more matter into these slightly denser regions. These quantum fluctuations were the seeds. They were the blueprints for the entire cosmic web. Every star, every galaxy, every great cluster of galaxies we see in the night sky owes its existence to a single random quantum fluctuation in that original vacuum magnified to cosmic proportions by inflation. We are in the most literal sense the children of quantum uncertainty. This brings us to the most profound and mind-bending idea of all. How do you get an entire universe with its trillions of galaxies and uncounted quadrillions of stars from nothing? How can you get something from nothing? This is the ultimate free lunch hypothesis. The idea is that the total energy of the entire universe might be zero. That sounds impossible. Look at all the stuff, the stars, the radiation, the matter that's all positive energy. But the universe also has gravity. Gravity is an attractive force. It pulls things together. To pull two galaxies apart, you have to add energy to the system. This means that the gravitational field itself can be thought of as containing negative energy. The math championed by physicists like Alan Guth suggests that the vast positive energy of all the stuff in the universe may be perfectly balanced by the vast negative energy of the gravity that holds it all together. If the total energy of the universe is zero, then you don't need a miracle to create it. You don't need to inject a universe's worth of energy from somewhere else. All you need is a quantum fluctuation, a random burp in the vacuum that borrows a bit of energy. But in this one special case, the fluctuation didn't just disappear. It created positive energy matter and negative energy gravity in perfect balance. The cosmic books were balanced. The loan was paid by the gravity it created. And in that instant, the process of inflation kicked in, grabbing that balanced zero energy bubble and expanding it into the vast, complex and beautiful universe we see today. We have spent our journey so far looking at the edges of our own universe, the 13.8 billion-year-old story of our own cosmos, the limits of what we can see. It is a story so vast it defies imagination. But now we must ask the most profound question of all: is our universe with its hundreds of billions of galaxies the entirety of reality? Or is it just one tiny part of something infinitely larger? This is the concept of the multiverse or parallel realities. For decades, this idea was pure science fiction. It was the territory of comic books and fantasy novels, a fun idea to play with, but not a serious scientific proposal. But in the last few decades, something has fundamentally changed. The multiverse is no longer just a philosophical or fictional idea. It has emerged as a potential and perhaps even necessary consequence of our most successful and accepted theories. The very mathematics we use to describe our own reality, the rules of the Big Bang and the laws of the quantum world, are now pointing beyond it. The first and perhaps most widely discussed model comes directly from the birth of our own universe. We believe that in the first trillionth of a second, our universe underwent a period of a hyper-fast expansion called cosmic inflation. It's what stretched our universe from a microscopic point to a vast expanse, smoothing it out and setting the stage for the galaxies we see today. But the physicists who developed this theory, like Alan Guth and Andre Linde, asked a critical question: what if the off switch was faulty? What if inflation stopped here in our region, allowing our universe to cool down and form stars, but it didn't stop everywhere else? This leads to the theory of eternal inflation. Imagine a vast cosmic ocean of energy constantly boiling and expanding at this incredible inflationary speed. Think of it as a massive foaming sea or a gigantic bubble bath. Every so often, in one tiny spot, the rapid inflation stops. A bubble forms. This bubble stops stretching, cools down, and becomes a universe complete with its own space-time and matter. That bubble begins its own slower expansion like the one we see. In this model, our entire 13.8 billion-year-old observable universe, all the galaxies, all the stars, everything we have ever known is just one bubble in this infinite foaming sea. The sea itself, the space between the bubbles, is still inflating constantly, spawning new bubble universes forever. The most staggering part of this idea is that these other bubbles and these other universes might not look like ours, the settings of physics. How strong gravity is, the mass of an electron, the speed of light might be set randomly in each new bubble. Most of these universes would be failures. They might collapse instantly, or expand so fast that no stars could ever form. They would be dead, sterile and empty. But with an infinite number of bubbles, you get infinite possibilities. That's one way to get a multiverse emerging from the science of the very big. But there is another completely separate path that comes from the science of the very, very small. This is the many worlds interpretation of quantum mechanics. Quantum mechanics is the set of rules that governs the universe on the smallest possible scale. And its rules are bizarre. It tells us that before you look at it, a tiny particle like an electron doesn't have a specific location. It exists in a superposition, a cloud of all its possible locations at once. When you measure it, the particle seems to choose one reality. For nearly a century, physicists argued about what this meant. The common view, the Copenhagen interpretation, was that all the other possibilities just vanished. They simply ceased to exist. But in the 1950s, a physicist named Hugh Everett proposed a radical, disturbing and beautiful alternative. He said the possibilities don't vanish, they all happen. When a quantum event forces a choice, say a particle can spin left or spin right, the universe itself splits in two. In one universe, the particle spun left. In another identical universe, it spun right. This isn't just for particles. Every time a quantum-level decision is made, the timeline branches. This means that right now, there is a version of you that decided not to listen to this. There is a universe where you turned left this morning instead of right. There's a universe where that tiny random mutation in your ancestors' DNA didn't happen. These parallel worlds aren't far away in space like the bubble universes. They're all around us, existing in the same space but completely separate, unable to interact. This view argues that reality is an infinitely branching tree, and we are just walking along one single branch. Both of these multiverse theories, the eternal inflationary bubbles and the quantum branching trees, help to answer one of the deepest and most troubling questions in all of science. Why is our universe so perfect for us? This is the fine-tuning problem. The laws of physics in our universe seem to be balanced on a knife edge, perfectly set up to allow for complexity, chemistry, and life. If the force of gravity were just a tiny bit stronger, the universe would have collapsed back on itself long ago. If it were a tiny bit weaker, gas clouds would never have pulled together to make the first stars. If the nuclear forces that hold atoms together were even slightly different, we wouldn't have carbon, the element that forms the basis of all known life. It all looks, for lack of a better word, designed. This is where the anthropic principle comes in. In its simplest form, this principle states that the universe must be compatible with us because we're here observing it. It is a selection bias. If our universe wasn't fine-tuned for life, we wouldn't be here to wonder why it was. The multiverse gives this principle real power. If there are infinite bubble universes, each with different physical laws, then it's not surprising that at least one would by pure chance have the right settings for life. We simply live in the one that won the cosmic lottery. It's not magic, it's statistics. We are here asking these questions because we're in the one reality where it's possible. In all the other dead universes, there is no one to notice. So is our reality just one stable bubble in a chaotic foam? Is it one path on an endlessly branching tree? We don't know. These ideas are at the very edge of what we can test. But they are not fantasies, they are the logical and perhaps unavoidable conclusion of our best theories. They suggest that the cosmos, the entirety of what is vastly larger, more complex and stranger than we ever dared to imagine. For nearly 400 million years after the Big Bang, the universe was dark. This period is known as the Cosmic Dark Ages. The entire cosmos was filled with a vast neutral fog of hydrogen and helium gas. There were no stars, no galaxies, and no planets. The universe was quiet, cold, and expanding, but it was not perfectly uniform. Thanks to the tiny quantum fluctuations from the moment of creation, some regions of this gas fog were just slightly denser than others. This tiny difference was all that was needed. In the dark, a patient and relentless force was at work. Gravity is weak, but it is persistent. In those slightly denser patches of gas, gravity had a slightly stronger pull. Over millions of years, this pull began to draw in more and more hydrogen and helium from the surrounding areas. The fog began to curdle, forming vast, swirling clouds of gas. As these clouds grew, their own gravity increased, pulling them inward, causing them to collapse and compress. As the gas in the center of a collapsing cloud was crushed, the pressure and temperature skyrocketed. The core of the cloud became a furnace reaching temperatures of millions of degrees. Eventually it became so hot and so dense that a new process ignited nuclear fusion. The hydrogen atoms, the simplest atoms in the universe, were slammed together with such force that they fused to create helium. This reaction released a tremendous burst of energy, light and heat. The first star was born. The cosmic dark ages were over. This moment, the cosmic dawn, was the instant the universe turned on the lights. These first stars, known to astronomers as population 3 stars, were nothing like our Sun. They were monsters. When our Sun formed billions of years later, the gas cloud that made it was polluted with heavier elements like carbon, oxygen and iron, which were created by previous generations of stars. These metals, as astronomers call everything heavier than helium, act like a cooling system, allowing gas cloud to fragment and form many smaller stable stars. The first stars had no metals. They were made of pure original hydrogen and helium. Without this cooling system, the collapsing gas clouds could not fragment easily. They just kept getting bigger and bigger, pulling in more and more mass until they finally ignited. The first stars were enormous, perhaps 100 to 300 times more massive than our own Sun. Because they were so massive, they were incredibly bright, shining with a brilliant blue-white light, perhaps millions of times brighter than the sun. But they lived fast and died young. A star that massive burns through its hydrogen fuel at a furious rate. While our sun will live for about 10 billion years, these first giants lasted only a few million years. Their death was as spectacular as their birth. They exploded in a cataclysmic event called a supernova. This explosion was not just an end, it was a factory. Inside the dying star's core, the intense heat and pressure of the explosion forged the first heavy elements. The hydrogen and helium were cooked into carbon, oxygen, silicon, and iron. These new elements, the raw materials for planets and for life, were blasted out into the cosmos. This star stuff seeded the surrounding gas clouds. The next generation of stars, population 2, would be born from this enriched gas, and when those stars died, they created even more metals. Our Sun is a population 1 star rich in elements forged in the hearts of long-dead ancestors. Every atom of carbon in your body, every atom of iron in your blood was created inside one of these ancient giant stars. While individual stars were lighting up the darkness, gravity was working on a much grander scale. The universe had an invisible scaffolding made of dark matter. This mysterious substance, which we cannot see, makes up about 85% of all matter in the cosmos. Just like the normal gas, this dark matter was also clumped together by gravity. It formed massive invisible halos, or wells, in space. The normal hydrogen and helium gas, feeling the intense gravitational pull of these halos, flowed into them like water into a valley. These vast gravitational wells became the nurseries for galaxies. Inside these dark matter halos, the gas collected, cooled, and collapsed, forming not just one star, but billions of them. The first protogalaxies were small, messy, and chaotic, full of new stars exploding and gas churning. But this was just the beginning. Gravity continued to pull these protogalaxies toward each other. Over the next billion years, the universe was a cosmic construction site. Small galaxies collided and merged, forming larger ones. These larger galaxies then merged to form even bigger ones. This process of hierarchical assembly is how the great cities of stars were built. Our own Milky Way galaxy is the result of countless such mergers over 13 billion years. At the very center of this cosmic construction, something even more extreme was growing. In the densest part of the gas at the heart of the dark matter halo, gravity was winning completely. When the most massive of the first stars died, they didn't just explode. Their cores collapsed under their own immense gravity, crushing matter down to an infinitely small point, a black hole. These were the seeds of monsters. In the chaotic gas-rich center of a new galaxy, these seed black holes had an endless buffet. They fed on the gas dust and even other stars that fell into them. As they fed, they grew. When two galaxies merged, their central black holes would spiral toward each other, and eventually merge too, forming an even larger black hole. Over time, these objects grew from a few hundred times the mass of the Sun to millions or even billions of times the mass of the Sun. They became supermassive black holes. For a time, as these black holes were feeding rapidly, the material swirling into them, the accretion disk, would heat up to millions of degrees, shining brighter than the entire host galaxy combined. These objects, known as quasars, are the most luminous things in the universe, and we can see them from billions of light years away, shining from the teenage years of the cosmos. Today we have discovered that nearly every large galaxy, including our own Milky Way, has a supermassive black hole at its center. These giants are not just artifacts. They are a fundamental part of the galaxy's life, shaping its growth, and a constant silent reminder of the power of gravity. For all their magnificent power, stars are not immortal. They are locked in a constant battle between the crushing inward force of gravity and the explosive outward pressure of nuclear fusion. As long as the star has fuel, fusion wins, keeping the star stable and bright. But fuel eventually runs out. For the most massive stars, those many times larger than our Sun, this end is not a quiet fade, but the most violent event in the universe, a supernova. These giants live fast and die young. Their immense gravity creates such intense pressure in their cores that they burn through their fuel at a frantic pace. They start by fusing hydrogen into helium just like our Sun. But when the hydrogen runs out, the core contracts, an outer shell of hydrogen ignites, and the star swells into a supergiant. The core, however, continues its journey. The pressure becomes strong enough to fuse helium into carbon. Then the carbon fuses into neon, the neon into oxygen, the oxygen into silicon. The star builds a core like a cosmic onion with layers of different elements, the heaviest ones closest to the center. Each new fusion stage provides a temporary reprieve, pushing back against gravity for a shorter and shorter time. The silicon fusing stage, for example, may last only a single day. This frantic process stops catastrophically at one specific element, iron. The crisis of a star's life is that iron is the ultimate nuclear ash. For all the elements before iron, fusing them together releases energy. This is the energy that holds the star up, but fusing iron atoms does not release energy. It consumes energy. When the star's core becomes iron, the furnace shuts off instantly. In less than a second, the star's source of power is gone. The outward pressure vanishes and gravity wins. This is the core collapse. The iron core, which might be larger than the entire planet Earth, implodes upon itself. With nothing to support it, the core collapses at nearly a quarter of the speed of light. In a fraction of a second, it shrinks to the size of a city, packing the mass of a sun into a space just a few miles across. It becomes an object so dense that a single teaspoon of it would weigh billions of tons. The outer layers of the star, billions of miles of gas, suddenly have the floor vanish from beneath them. They begin to fall inward, crashing down onto the newly formed ultra-dense core. This core is now so dense it cannot be compressed further. The infalling material hits this core, which has become a neutron star, and bounces. This colossal rebound creates a shockwave of unimaginable power. The shockwave blasts outward, racing through the collapsing layers of the star, heating them to billions of degrees. This is the explosion we see as a supernova, an event so bright it can outshine its entire host galaxy for weeks. But the supernova is more than just a bright light, it is the cosmic forge. During the star's life, it only created elements up to iron. So where do all the other elements in the universe come from? Where do we get silver, gold, platinum, or the uranium that powers nuclear reactors? They are created in the final violent seconds of the star's death. The supernova explosion is an environment of chaos flooded with pure energy and particles called neutrons. As the shockwave rips through the star's layers, it smashes atoms apart and floods the iron nuclei with these neutrons. The iron atoms absorb neutron after neutron, becoming bloated and unstable. After the explosion, these unstable atoms begin to decay. Neutrons inside them change into protons, and the element changes its identity. An iron atom which has 26 protons might transform into silver, 47 protons, or even gold, 79 protons. Almost every precious metal we value, every element heavier than iron, was forged in this rapid neutron capture process, a process that can only happen in the extreme environment of a dying star or the collision of two neutron stars. At the same time, the explosion scatters all the other elements the star created during its life. The calcium from its shell burning the carbon, and oxygen from its earlier life, and the iron from its dead core are all thrown violently into space. This brings us to the most important function of a supernova: cosmic recycling. The universe after the Big Bang was simple. It contained almost nothing but hydrogen and helium. It was the first generation of stars that fused these light elements into heavier ones. But if those elements stayed locked inside the stars, they would be useless. The supernova explosion is the universe's delivery mechanism. The blast wave seeds the surrounding gas clouds with all the new heavy elements. This enriched gas cloud, now full of carbon, oxygen, silicon, iron, and gold, becomes a stellar nursery. It is the raw material for the next generation of stars and, crucially, planets. Our own solar system formed from one such cloud. The Sun is a second or third generation star. We know this because of what we are made of. This is the most profound connection we have to the cosmos. When you look at your own hand, you are looking at atoms that were forged in the heart of a star that died billions of years ago. The iron in your blood, which allows you to carry oxygen, was the final ash in the core of a massive star, the very element that triggered its collapse. The calcium in your bones and teeth giving you structure was created in the final moments of that star's life. The gold on your finger, the silver in your electronics, the carbon that forms the basis of all life, all of it was created and scattered by these cosmic forges. We are not just living in the universe, we are the universe. We are quite literally the dust of ancient stars, given the chance to live, think, and look back up at the sky, wondering where we came from. The death of a star is not an end. It is the necessary, violent, and beautiful beginning of everything that matters. The journey into the abyss begins not with a wall, but with a whisper. In our exploration of general relativity, we saw that gravity is the bending of space-time by mass. The more massive and dense an object, the deeper the gravity well it creates. For a normal star, this well is a slope you can climb out of. If you have a powerful enough rocket, you can achieve escape velocity and break free. A black hole is what happens when this well becomes a bottomless pit. The event horizon is the lip of this pit. It is not a physical surface, you can't touch it or stand on it. It is quite simply the precise boundary in space where the gravitational pull becomes so strong that the escape velocity equals the speed of light. Because nothing in the universe can travel faster than light, this boundary is the ultimate point of no return. If you were in a spaceship safely orbiting a black hole, you could watch a probe fall toward it. As the probe approached the event horizon, something strange would happen. From your perspective, time for the probe would slow down. It would seem to take minutes, then hours, then centuries to cross that invisible line. It would appear to freeze in place, growing dimmer and redder, as the intense gravity stretched its light waves until it faded into nothing. You would never actually see it cross. But for the probe itself, or an astronaut inside the experience, would be completely different. They would feel no bump here, no alarm. They would sail right across the event horizon in a single perfectly normal moment, unaware that they had just sealed their fate. From that instant forward, all paths, every possible direction they could try to move, would only point inward toward the center. The fabric of space-time itself would be rushing inward faster than light, carrying them to their doom. The singularity. Once you cross the event horizon, your destination is guaranteed. All the matter that has ever fallen into the black hole, entire stars, gas clouds, and unlucky astronauts is crushed into a single central point. This point is called the singularity. It is a place where the rules of our universe are completely and totally shattered. In this one spot, our current understanding of physics stops working. According to Einstein's equations, the singularity is a point of zero volume and infinite density. The curvature of space-time becomes infinite. Time itself as we know it comes to an end. When physicists see the word infinity in an equation, it's a red flag. It doesn't mean the density is actually infinite. It means our theory, general relativity, is no longer adequate to describe what is happening. It's like trying to use a city map to navigate the entire ocean. To truly understand the singularity, we need a new theory, one that combines Einstein's gravity with the rules of the very small quantum mechanics. We need a theory of quantum gravity, the holy grail of modern physics, the information paradox. For decades, black holes were seen as simple cosmic vacuum cleaners. They had three properties you could measure from the outside: their mass, how heavy they are, their spin, how fast they are rotating, and their charge. That's it. This idea is called the no-hair theorem. Black holes are perfectly bald with no other complex features. This simplicity created a terrifying problem, the information paradox. Here is the conflict which represents the greatest disagreement in all of physics. Rule 1. Quantum mechanics. The most fundamental law of quantum physics states that information can never be destroyed. It can be hidden, scrambled, or burned, but it never truly vanishes. If you burn a book, you might think the information in the words is gone, but in theory, if you could collect every single particle of smoke, ash, and heat, you could reconstruct the book. The information is still there. Rule 2. General relativity. Einstein's theory says that when you throw the book into a black hole, the information is gone forever. The black hole only gets heavier. The story inside the book, the arrangement of its atoms, is completely erased from the universe, hidden behind the event horizon. So what happens? Does the information get destroyed violating quantum mechanics, or is it somehow preserved violating general relativity? Hawking radiation. The puzzle became even more intense thanks to Stephen Hawking. In the 1970s, Hawking did something brilliant. He applied the rules of quantum mechanics to the edge of a black hole, the event horizon. He realized that empty space is not truly empty. On a microscopic quantum level, it is a bubbling foam of virtual particles. Pairs of particles, one matter, one antimatter, constantly pop into existence and then immediately collide and destroy each other. This happens everywhere all the time. Hawking wondered what happens if a pair of these virtual particles pops into existence right on the event horizon. In this rare case, one particle might fall into the black hole while the other particle escapes into space. The particle that escapes becomes real and carries energy away from the black hole. This stream of escaping particles is known as Hawking radiation. Where does this energy come from? It comes from the black hole itself. The black hole pays for the escaping particle by losing a tiny bit of its own mass thanks to Einstein's famous E=mc² energy and mass are interchangeable. This led to a stunning conclusion. Black holes are not permanent, they evaporate. This process is incredibly slow. For a black hole the mass of our sun, it would take longer than the current age of the universe to evaporate. But eventually they will shrink, lose all their mass, and disappear in a final flash of radiation. This discovery made the information paradox worse. If the black hole eventually disappears, what happens to all the information, the book, the star, the astronaut that fell inside? Is it truly destroyed forever? Hawking initially believed it was, which meant quantum mechanics must be wrong. The holographic principle and firewalls. This paradox is still not solved, but it has led to some of the wildest and most profound ideas in physics. Two leading solutions attempt to save the information. First is the holographic principle. This idea, championed by physicists like Leonard Susskind and Gerard 't Hooft, suggests that the information never actually makes it inside the black hole. Instead, as the book falls toward the black hole, its information is imprinted or smeared onto the two-dimensional surface of the event horizon, like a computer's hard drive. The event horizon in this view is a giant hologram that contains all the data for everything that ever fell in. Then, as the black hole evaporates via Hawking radiation, that radiation which originates at the horizon picks up the scrambled information and carries it back out into the universe. The information is saved. It's not destroyed, just heavily encrypted and very hard to read. Second is the firewall concept. This solution is more violent. It agrees that information must get out, but for the information to be released fast enough as the black hole evaporates, it creates a deadly side effect. This theory says that the event horizon is not a calm, peaceful boundary. Instead, it is a firewall, a region of intense high-energy particles that would instantly incinerate anything that tries to cross it. This idea saves quantum mechanics. Information is saved, but it destroys Einstein's theory of general relativity. It violates his equivalence principle, which stated that falling into a black hole should feel smooth and unremarkable. Today we are still trapped between these possibilities. Is the edge of a black hole a gentle hologram that stores our past, or is it a raging firewall that destroys our future? In trying to understand the black hole, we have been forced to question the very nature of reality information and the fabric of the cosmos itself. For all of human history, our universe consisted of a handful of planets, all named, all familiar, all circling our own sun. We knew Mercury, Venus, Mars, Jupiter, and Saturn. Later we added Uranus and Neptune, but they were ours. They were our local family. For thousands of years we looked up at the points of light we call stars and asked a question that defines our species. Are we alone? We wondered if those distant suns also had families of their own. Were there other Earths, other Jupiters? Or perhaps were there types of worlds we had never even imagined? It was a question for philosophy and science fiction. Until 95, in 95 the question changed forever. It moved from philosophy to fact. We found one, and it was nothing like we expected. We assumed that if we found other solar systems, they would look like ours, small rocky planets close to the star and giant gas planets far out in the cold darkness. The first major planet confirmed around a sun-like star, 51 Pegasi b, shattered that assumption. It was a monster. This was a planet with the mass of Jupiter, our own solar system's king. But here's the part that baffled everyone. It orbited its star in just 4 days. Our Jupiter takes 12 years to make one lap. This new planet was so close to its star that its surface temperature would be over 1,000 degrees Celsius. It was a world of boiling metal larger than anything in our inner solar system, orbiting closer than Mercury. We called this new class of worlds the hot Jupiters. Their discovery was a shock to the system. It told us that the universe was far more creative and far more violent than we had dared to imagine. It proved that planets are not necessarily born in the orbits they keep. They can migrate. These giant worlds were likely born far out just like our Jupiter, but something caused them to spiral inward, crashing through their own inner solar systems, destroying any smaller Earth-like worlds that might have been there, before settling into a blazing hot orbit right next to their sun. Finding them was the first step, but it immediately raised a new question. How do you even find a planet hundreds of light years away? You can't see it. It's an object the size of a marble next to a searchlight that is miles away. We had to invent new, incredibly clever ways to find these hidden worlds. The first, and the one that found that initial hot Jupiter, is called the wobble method. Think of it this way. When you walk a large, excited dog on a leash, the dog doesn't just circle you. The dog is big enough to pull on you, making you wobble back and forth a little bit. A planet does the same thing to its star. The star's gravity holds the planet in orbit, but the planet's gravity, especially a big one, pulls back. It makes the star execute a tiny, almost imperceptible wobble. We can't see the wobble itself, but we can see its effect on the star's light. As the star wobbles toward us, its light waves get squished, making them appear slightly bluer. As it wobbles away from us, the light waves get stretched, making them appear slightly redder. This tiny rhythmic shift in colour, this stellar dance, tells us an invisible partner is there. It tells us the planet's mass and how long its year is. But there is a second method, one that has been even more successful and has found thousands of planets. This is the transit method. Imagine you are looking at a powerful distant streetlight. If a tiny moth flies directly in front of that light, you won't see the moth, but you might notice the light dim by a tiny fraction for just a moment. The transit method works exactly the same way. Space telescopes like the revolutionary Kepler mission, and now the TESS mission, are built to do one thing: stare. They stare at hundreds of thousands of stars, simultaneously patiently monitoring their brightness. They wait for a planet whose orbit just happens to be perfectly aligned from our point of view to pass directly in front of its star. When it does, the star's light dims. It might only dim by 1%, or for a tiny rocky planet by less than 1/100th of 1%. But it dims, and if it dims with perfect regularity, say every 10 days or every 300 days, we know something is orbiting there. This method is brilliant because it tells us something the wobble method can't. It tells us the planet's size. And if you know its size from the transit and its mass from the wobble, you can calculate its density. You can know if you're looking at a fluffy gas giant or a dense rocky world like Earth. Suddenly, we had a catalogue. In just 3 decades, we have gone from knowing of only our 8 planets to confirming over 5,000 exoplanets. The sky is full of them. So the next question becomes, which ones could host life? This brings us to the search for the habitable zone. You might know this better as the Goldilocks zone. Every star has a region around it that is not too hot and not too cold, but just right for life as we know it. If a planet is too close to its star, any water on its surface will boil away into the space. If it's too far, any water will freeze into a permanent block of ice. But in that perfect temperate ring of the habitable zone, the temperature is right for liquid water to pool on a planet's surface. And as far as we know, liquid water is the one non-negotiable ingredient for life. Finding a planet in the habitable zone is the holy grail of exoplanet hunting. We have already found dozens. We have found super-Earths, which are rocky worlds larger than our own. We have found Earth-sized worlds. We have even found entire systems like TRAPPIST-1, a small cool star that has 7 rocky planets, at least 3 of which are in its habitable zone. But finding a planet in the right place isn't enough. A planet can be in the zone and still be dead. Mars is in our habitable zone, but it's a frozen desert with a thin atmosphere. We have to take the final, most difficult step. We have to search for biosignatures. A biosignature is simply a sign of life. It's a clue in a planet's atmosphere that tells us something biological is happening on the surface. We can't go there to collect samples, but we can use our new powerful telescopes like the James Webb Space Telescope to sniff their air. How we use the transit method again. When a planet with an atmosphere passes in front of its star, a tiny sliver of starlight filters through that atmosphere before it reaches our telescopes. By analysing that light, we can see the chemical fingerprints of the gases in that planet's air. What are we looking for? We are looking for an atmosphere that is out of balance. A dead, sterile planet should be in a state of chemical equilibrium. A living planet is messy. Life constantly breathes, eats, and pollutes. It pumps gases into the air that shouldn't be there. On Earth, for example, our atmosphere is filled with oxygen. Oxygen is a very reactive gas. It loves to bind with other elements. It shouldn't exist in our atmosphere for long on its own. The only reason our air is 21% oxygen is because for billions of years, plants and bacteria have been constantly producing it through photosynthesis. At the same time, we have methane in our air, much of it produced by microbes. Oxygen and methane react with each other and should cancel each other out. Finding both of them in the same atmosphere is a powerful sign that 2 different biological processes are constantly replenishing them. This is the search we are undertaking right now. We are moving from simply counting planets to characterizing them. We are hunting for oxygen, for methane, for carbon dioxide and water vapor. We are looking for the telltale chemical imbalance that screams life. We are the first generation in human history to know for a fact that our galaxy is teeming with worlds, and we may very well be the first generation to get an answer to that ancient question. We are no longer just looking at the stars and wondering. We are looking and we are measuring. We've spent our time looking out at the cosmic ocean, at the islands of light we call galaxies and the furnaces we call stars. We've seen how they are born and how they die, but now we turn our gaze around. We look back at the place we are standing. We are looking for one specific unremarkable cloud of dust orbiting one average yellow star in a quiet neighbourhood of the Milky Way. 4.5 billion years ago, this cloud collapsed, ignited and formed our solar system. We've discussed the giants like Jupiter that bullied the other planets into place. Now we focus on the third rock from the Sun. Today we see it as a pale blue dot, a gentle oasis of life suspended in the vast, terrifying darkness. But if we could travel back in time, we wouldn't recognise our own home. The newborn Earth was not a garden, it was a hell. We call this early period the Hadean Eon, named after Hades the underworld. It was a world of fire. The planet had only just formed, and it was a boiling ball of molten rock, a global ocean of magma. The atmosphere was not the clear blue sky we know. It was a thick toxic blanket of steam, carbon dioxide, methane, and ammonia. There was virtually no free oxygen. You would suffocate instantly. And the solar system was still a chaotic construction site. This early Earth was under constant violent assault. This wasn't just small meteorites. This was an era we call the Late Heavy Bombardment. Asteroids the size of cities and countries, leftovers from the solar system's formation, slammed into our planet over and over again. These impacts were so powerful they would have sterilized the entire globe, boiling off any oceans that tried to form and keeping the surface a molten, lifeless cauldron. This was a sterile, chaotic, violent world. How did it become our world? The first crucial event was perhaps the most violent of all. We believe that in these early chaotic days, Earth didn't orbit alone. It had a sibling, a planet roughly the size of Mars, which scientists have named Theia. Their orbits crossed. In a cataclysm that defies imagination, Theia smashed into the molten Earth. This wasn't just an impact, it was a world ender that became a world creator. The collision was so immense that it tilted the Earth on its axis, it vaporized Theia, and a huge chunk of our own planet, throwing a massive cloud of superheated rock and debris into orbit. Gravity, the force that builds everything, went to work. This ring of debris slowly, over maybe just a few thousand years, clumped together. It cooled, it solidified, and it became our companion. Our moon. We often take the moon for granted. It's a beautiful light in the night sky, a symbol for poets. But the moon is not just decoration. It is our silent guardian. Its creation is perhaps the single most important reason we are here. First, the moon stabilized our planet. Planets wobble. Without the moon, Earth's axial tilt, the angle that gives us our seasons, would be chaotic. It might swing wildly over millions of years, causing catastrophic climate change. One moment, the poles would point straight at the sun, creating unimaginable heat. The next, they would be plunged into an extreme ice age. Complex life cannot evolve in that kind of chaos. The moon's immense gravity acts like a steadying hand. It locks our planet at a stable tilt about 23.5 degrees, which gives us the predictable, reliable seasons that life has depended on for billions of years. Second, the moon slowed us down. Right after the impact, the moon was much, much closer to Earth, and the Earth was spinning incredibly fast. A single day might have lasted only 6 hours, but the moon's gravity has been pulling on the Earth, acting like a cosmic brake. Over billions of years, it has slowed our rotation to the gentle 24-hour cycle we have now. Finally, the moon stirred the pot. Back when it was so close, its gravity created tides that were unlike anything we see today. They weren't just a few feet high, they were colossal, perhaps hundreds of feet high. These were mountains of water that washed back and forth across the globe, churning the early oceans. This constant massive mixing of water and minerals was essential. It created the primordial soup. The bombardment eventually slowed down. The planet finally cooled enough for the steam in the atmosphere to rain down, forming the first oceans. These oceans were not blue, they were likely a toxic iron-filled brown. But they were here, and thanks to the moon they were being mixed. We now have a stage, a stable planet with liquid water and a steady climate. We have the ingredients delivered by volcanoes and comets, our carbon, hydrogen, nitrogen, oxygen. We have a primeval soup full of non-living chemistry. The next step is the greatest mystery in all of science. It is the boundary between nothing and something, the move from chemistry to biology. We call it abiogenesis, the origin of life from non-life. We still don't know exactly how it happened. Perhaps it was in a warm, shallow pond where the sun's energy concentrated these chemicals, or maybe it was in the deep, dark ocean next to a hydrothermal vent where superheated, mineral-rich water blasted out from the planet's core. But somehow, somewhere in that chemical soup, a molecule formed by pure chance. It probably wasn't DNA deoxyribonucleic acid. It was likely a simpler cousin like RNA ribonucleic acid. This molecule wasn't alive. It couldn't think. It couldn't see. But it had one magical accidental property: it could make copies of itself. This was the spark. The moment a piece of chemistry learned to replicate, everything changed. It was no longer just chemistry, it was inheritance. It was evolution. The first replicators were messy. They made mistakes or mutations. Most mistakes were useless. But every so often a mistake made the next copy slightly better at replicating. Maybe it was more stable. Maybe it was faster. Those better copies made more copies. This was natural selection in its most basic form, acting on pure chemicals. Over millions of years, these simple replicators learned to build protective bubbles around themselves, the first cells. They became the ancestors of everything that has ever lived. We call this ancestor Luca, the last universal common ancestor. You, me, the trees outside of the birds in the sky, the bacteria in the soil, we all share the same family tree. Our oldest relative is that first impossible spark of life that emerged in the darkness of the early Earth. For billions of years, that was it. Life was just single cells floating in the ocean. But this life began to change the planet. A new kind of bacteria, cyanobacteria, evolved a new trick. It learned to eat sunlight. We call it photosynthesis, and as a waste product, it released a gas. A gas that was at the time a deadly poison to almost everything else, oxygen. These tiny microbes pumped so much oxygen into the oceans and the air that it changed the world. It rusted the iron out of the seas, turning the brown oceans blue. It cleared the methane haze from the sky, turning the sky blue. It created the very air we now breathe. Life did not simply appear on Earth. Life built the Earth we know. It terraformed its own home. This is the miracle of the pale blue dot. It is not just a rock with water on it. It is a single unified system where the geology and the biology are linked. The rocks, the air, the water, and the life us are all part of one giant, breathing, evolving story. We often take the flow of time for granted. It moves relentlessly in one direction. We are born, we grow older, and we cannot reverse the process. This one-way journey is often called the arrow of time. It is perhaps the most fundamental experience of our reality. But why does it exist? Why do we remember the past but not the future? Physics equations strangely don't really care about the direction of time. Most laws of nature would work just as well if time ran backward. A planet orbiting a star would follow the same path, yet in our world a broken glass never reassembles itself. An old person never grows young. The answer to this profound puzzle seems to lie in one of the most important rules of the universe, the second law of thermodynamics. This law introduces a concept called entropy. Entropy is simply a measurement of disorder or messiness. The second law states that in any closed system like our universe as a whole, entropy always increases. Things move from a state of order to a state of disorder. Think of your room. It is easy for it to become messy, a state of high entropy. It requires effort and energy to clean it and make it organized, a state of low entropy. A cup of hot coffee will always spread its heat out into the cooler room. It will never spontaneously gather the room's heat to become hot again. The mixed state coffee cooled room slightly warmer is more disordered than the organized state heat in one place, cold in another. This scientists believe is the arrow of time. Time moves forward because the universe is moving toward a state of greater disorder. The past is simply the time when the universe was more orderly. The future is the time when it will be more disorderly. We remember the past because the past was a state of lower entropy. All the complex structures we see, stars, planets, and even our own bodies are temporary islands of order in a cosmic ocean that is constantly moving toward maximum entropy. This, however, leads to an even deeper mystery. If the universe is always getting messier, it must mean that it began in a state of almost perfect, unbelievable order. This is the great puzzle of the Big Bang. For the universe to have the arrow of time, it must have started in a state of incredibly low entropy. All the energy and matter in the entire observable universe were packed into a space smaller than an atom, not in chaos but in a highly specific organized configuration. Why? We do not know. If the Big Bang had started in a normal high-entropy chaotic state, which is statistically far more likely, the universe would just be a boring uniform soup of particles. There would be no flow of time, no work to be done. No stars could form, no planets, no life. The fact that the universe had this special low-entropy beginning is the reason we have an arrow at all. It is the reason yesterday is different from tomorrow. This brings us to the fabric of reality itself. It seems the universe is not just any universe, it appears to be special. The laws of physics that govern everything are built upon a set of fundamental numbers or constants. These constants are the settings for our reality. They include the speed of light, which is the ultimate speed limit. They include the gravitational constant, which determines the strength of gravity, how hard a star pulls itself together, or how a planet orbits. They include the strength of the force that holds atoms together, the strong nuclear force, and the precise mass of tiny particles like the electron. Here is the astonishing part that these numbers appear to be fine-tuned. It is as if our universe is a complex machine with dozens of dials, and each dial has been set to the exact precise value necessary for complex structures like us to exist. If you were to change any of these dials, even by a tiny, tiny amount, the universe would be unrecognizable. Let's imagine tuning these dials differently. If the gravitational constant were just a little bit stronger, stars would burn their fuel incredibly fast and violently. They would burn out in millions of years, not billions. This is not nearly enough time for the slow process of evolution to occur on any orbiting planets. If gravity were just a little weaker, stars and galaxies might never have formed at all. The universe would just be a cold, thin cloud of gas. What about the force that holds atomic nuclei together? If it were slightly weaker, it could not hold more than one proton. The only element in the universe would be hydrogen. Without elements like carbon, oxygen and iron, there would be no planets, no water and no life. If this force were slightly stronger, protons would have fused together so efficiently in the Big Bang that all the hydrogen would have been used up. Hydrogen is the main fuel for stars. No hydrogen, no stars. Even the expansion of the universe is balanced on a knife edge. If the initial push from the Big Bang had been slightly weaker, gravity would have pulled everything back together in a big crunch long before life could form. If the push had been slightly stronger, the universe would have expanded so quickly that matter would never have had the chance to clump together to form galaxies. The universe seems perfectly set up for life. This incredible fine-tuning is one of the biggest mysteries in science. Why are the rules so perfect? There are a few possible, though mind-bending explanations. Some scientists suggest it is just a brute fact. The universe is the way it is, and we are just incredibly lucky. Others find this unsatisfying. They propose the multiverse hypothesis. Perhaps there are an infinite number of universes, each one created with different random settings for these constants. In most of these universes, the rules do not allow for life. They are sterile, dead places. We, by definition, must find ourselves living in the one universe where the dials just happen to be set correctly for us to exist. We won the cosmic lottery. And finally, some argue this points to a deeper meaning. Perhaps even a designer who set the dials with the intention of creating complexity and life. Whatever the answer, exploring these constants reveals that the fabric of reality is not only strange, but it is also profoundly connected to our own existence. The rules that define the cosmos, from the flow of time to the strength of gravity, are the very rules that make it possible for us to be here looking back and wondering about it all. For centuries, physics has operated on a powerful, if slightly fractured, foundation. We have built two magnificent pillars of understanding. On one side, we have Albert Einstein's general theory of relativity. This is the ultimate macro theory. It describes the universe of the very large, the graceful dance of planets, the curving of starlight, the crushing pull of black holes. Relativity gives us a picture of space and time as a smooth, continuous fabric, a space-time that bends and warps in the presence of matter, which we then experience as gravity. It is deterministic, elegant, and has been proven correct time and time again on the cosmic scale. On the other side, we have quantum mechanics. This is the micro theory, the bizarre and wildly successful set of rules for the very small. It governs the world of atoms, electrons, and photons. Unlike the smooth predictability of relativity, the quantum world is fuzzy, chaotic, and based on probabilities. In this realm, particles can be in multiple places at once, and energy is not continuous but comes in discrete tiny packets called quanta. This theory is the foundation of all modern technology, from our phones to our computers to medical lasers. For most everyday situations, this division is fine. An astronomer calculating the orbit of Jupiter does not need to worry about the quantum state of its atoms. A chip designer figuring out electron behavior does not need to consider the curvature of space-time, but this piece is shattered at the extremes. There are two places in the universe where the very large and the very small are forced to meet the singularity at the center of a black hole, immense gravity crushed into an infinitely small point, and the very beginning of the universe. The Big Bang, the entire universe with all its mass contained in a space smaller than an atom. When we try to use our two great theories in these places, the math breaks. The equations for relativity and quantum mechanics, when combined, produce nonsense. They return answers like infinity, which is nature's way of telling us our theory is wrong. This is the central crisis of modern physics. We have two sets of rules for the same universe, and they contradict each other. This has launched the holy grail of modern science, the search for a theory of everything. This would be a single unified framework, perhaps a single elegant equation, from which both relativity and quantum mechanics would naturally emerge. It would be the final theory explaining all the fundamental forces and particles of nature. Currently, there are two main candidates in this hunt, two very different paths up the same mountain. The most famous is string theory. String theory proposes a radical and beautiful idea. At its core, it suggests that if you could zoom in on any particle, an electron, a quark, a photon, you would find it is not a point at us all. Instead, it is a tiny, vibrating one-dimensional loop of energy, a string. The magic of this idea is in the vibration. Just as a single violin string can play many different notes, a C, a G, and E, by vibrating at different frequencies, these fundamental strings can also vibrate in different modes. A string vibrating one way would appear to us as an electron. The same string vibrating a different way would appear as a photon. A third vibration would be a quark. In this view, all the diverse particles we see are just different notes played on the same underlying string. The greatest triumph of string theory is that without even trying, its mathematics naturally predicts a particle with the exact properties of the graviton, the long-sought hypothetical particle that carries the force of gravity. In this way, string theory seems to effortlessly unite the quantum world of particles with Einstein's world of gravity. But it comes at a price. For the math to work, string theory requires that the universe does not have just the three spatial dimensions we see: length, width, height, plus one of time. It requires that the universe has 10 or 11 dimensions. The proposed solution is that these other dimensions are curled up, compactified so tightly that they are billions of times smaller than an atom, completely invisible to us in our current experiments. This remains its biggest unproven hurdle. The other major contender is loop quantum gravity, or LQG. This theory takes a completely different approach. Instead of focusing on the particles, it focuses on the fabric of space-time itself. LQG asks, what if Einstein was only half right? What if space-time is smooth on large scales but chunky or pixelated at the smallest possible level? Loop quantum gravity quantizes space. It suggests that space is not an empty continuous void, but is built from discrete indivisible units like atoms of space. These are loops or networks of geometry, each one at the smallest possible size, known as the Planck length. You cannot have a distance smaller than this, just as you cannot have less than one quantum of energy. This idea elegantly solves one of physics' biggest problems, the singularity. In a black hole, matter cannot be crushed to an infinitely small point because there is a smallest possible pixel of space. It can only be crushed to the Planck size. The same goes for the Big Bang. LQG suggests the universe may not have started from an infinitely dense point, but may have bounced from a previous universe that had collapsed. LQG's main challenge is the opposite of string theories. While it provides a beautiful quantum picture of gravity and space, it has struggled to incorporate the other forces like electromagnetism and to explain how time itself flows. As physicists hunt for this ultimate code, a fascinating connection has emerged linking the cosmos not just to atoms but to biology. What, after all, is life? For a long time, life seemed to be a special exception to the rules of physics. The second law of thermodynamics states that everything in the universe tends toward decay and disorder. This is called entropy. Stars burn out, mountains erode, and coffee gets cold. Yet life is the opposite of this. Life is a pocket of incredible order. A human brain or the complex cells of a leaf are patterns of staggering complexity. How can physics, which loves disorder, create something so organized? The modern view is that life does not defy the second law. It is the ultimate expression of it. A living thing is not a closed system. We are dissipative structures. We maintain our own internal order by taking in ordered energy like sunlight or food and dissipating it, releasing a massive amount of disordered energy heat back into the environment. A plant, through photosynthesis, takes in high-energy sunlight and releases low-energy heat. In the process, it creates order in itself, but the total entropy disorder of the universe increases more than if the plant wasn't there. Life in this view is a tool the universe uses to increase entropy faster. This leads to a profound idea: perhaps life is not a lucky chemical accident. Perhaps it is an inevitable consequence of physics. When you have a planet like Earth being flooded with a powerful energy source like the Sun, physics will favour any arrangement of atoms that gets very good at dissipating that energy. Over time, matter will spontaneously organise itself into more and more complex structures, from simple molecules to cells to entire ecosystems, for the simple purpose of being a better conduit for energy. In this light, life is the universe's most complex and beautiful way to obey its own most fundamental law. The hunt for a theory of everything is not just about black holes and strings. It is about finding the one story that connects the Big Bang to the atoms in our bodies and explains how and why we are here to wonder about it all. We have built a stage of unimaginable proportions. We have 13.8 billion years of cosmic history, hundreds of billions of galaxies, and trillions upon trillions of planets. The stage is set. but it is empty. It is just physics and chemistry. The next step in our journey is the strangest of all. It is the transition from geology to biology. On at least one of these small rocky worlds, the inert chemicals floating in the water began to organize. They formed patterns that could copy themselves. Life had begun. But this too is not the final marvel. For billions of years, life on Earth was simple little more than single-celled slime. The emergence of complex life animals that can move and hunt and think is another hurdle so high it boggles the mind. This is the great mystery of our existence, the shadow that hangs over our search for others, the great filter. It's the idea that life might be common, but intelligent complex life is impossibly rare. Perhaps there are bottlenecks, cosmic obstacles that almost no life can pass through. Maybe the jump from a single cell to a multi-celled animal is one. Maybe the invention of language is another. Or perhaps the filter is still ahead of us, the tendency for intelligent species to destroy themselves with their own technology. When we look at the silence of the universe, we have to wonder, have we passed the great filter, or are we just about to face it? And what of intelligence itself? We often see evolution as a ladder climbing purposefully towards us, but that is not true. Evolution has no goal. Dinosaurs dominated this planet for 165 million years, and they never built a telescope. Intelligence, our specific brand of self-aware abstract questioning as intelligence, seems to be a bizarre evolutionary accident, a rare spin of the cosmic dice that produced a creature that could not only survive but could understand. This leads us to the final deepest mystery. It is one thing to be intelligent like a computer that can solve a problem. It is another thing entirely to be conscious. What is this experience? It is not the what of the brain, the firing of neurons and the flow of chemicals. It is the feeling of being, the experience of the color red, the sadness in a piece of music, the simple awareness that you are you. This is the hard problem. Science has no definitive answer. Where does this inner world come from? Some scientists are exploring theories that sound like science fiction. The integrated information theory suggests that consciousness is not a thing but a property of complex interconnected systems. It suggests that any system that can integrate a high amount of information like our brains will by its very nature feel like something. A simpler, perhaps more profound idea is panpsychism. This is the ancient belief that consciousness is not special. It is not something that brains create. Instead, it is a fundamental property of the universe woven into the fabric of reality, just like mass or gravity. In this view, an electron doesn't think, but it has a tiny primitive spark of experience. And when billions of these particles are organized into a complex structure like a human brain, those tiny sparks combine and ignite into the blazing fire of human consciousness. If this is true, it changes everything. It means the universe is not a dead place that accidentally grew a thinking mold. It means the universe has been awake in some small way from the very beginning. And it leads us to the most staggering thought of all. We are made of stardust. The iron in our blood, the calcium in our bones, these were forged in the hearts of dying stars. These atoms wandered the galaxy for billions of years. Now they have assembled into us. The universe through us has begun to wake up. Those atoms, which were once dumb, inert matter, are now arranged in a way that they can look back out at the stars and wonder where they came from. We are the cosmos made conscious. We are the universe finally becoming aware of itself. The music softens, becoming a gentle, slow and resonant hum like the sound of deep space. And so our long journey through the night comes to an end. We have travelled from the very beginning, from a moment of infinite density and heat. We watched as that energy cooled into the first particles, and those particles became the first atoms. We saw those atoms pulled together by gravity to ignite the first stars, and we saw those stars explode, seeding the void with the heavy elements of life. We have seen those elements form new worlds, and on at least one we have seen them come together in a miracle of chemistry to form life. We have seen that life struggle, evolve and survive against all odds, and finally we have seen that life become aware. Here you are, lying in the dark at the end of this journey. You are the product of 13.8 billion years of cosmic evolution. You are not a visitor here. You are not separate from the universe. You are the universe. You are stardust given life. You are matter given a voice. You are the laws of physics given the ability to ponder themselves. The simple fact that you are here in this moment is the most profound miracle we have yet discovered. The statistical probability of your existence of this specific arrangement of atoms that is you is so close to zero it is functionally impossible. And yet here you are. As you close your eyes, feel the weight of that. Feel the connection. The darkness of the room is not empty. It is the womb of the cosmos. It is the deep, quiet night from which all things came and to which all things will return. You are a child of this universe. You are its way of thinking, its way of feeling, and its way of dreaming. Now it is time for the universe to sleep.